Hello, good morning, students. Today, one of the important questions for the board exams in the current electricity chapter, that is, state Kirchhoff laws for electrical network. Using these laws, deduce the condition for balance in the wheatstone bridge. That is the question. For this question, you have to write in simple manner. First of all, for this answer will be number one, Kirchhoff current law. There are two laws: Kirchhoff current law, Kirchhoff voltage law. That is first law and second law. So first of all, first we discuss about the Kirchhoff first law. That is Kirchhoff, Kirchhoffs, Kirchhoff current law. So according to this law, algebraic sum of currents at a junction is equal to 0. Simple manner, the algebraic sum of currents at a junction is equal to 0. So you can write here, say this, for example, this is a junction, Dornakal junction, let us say. So many trains are coming and going. Incoming trains can be represented with the inside towards the center junction. Outgoing trains will be away from the junction. This is junction. Say these are the current trains, electricity trains, I1, I2, I3, I4 and I5. Say algebraic sum means incoming can be considered as positive, outgoing is negative. Let us say, that means we can say I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. Other words, you can say, if you take that side, it will becomes positive. Sum of the incoming currents is equal to sum of the outgoing currents. That is also you can write. So in this simple manner I can write here. Next, this is about the Kirchhoff current law. Here it holds good, it obeys, you have to write, better to write this point. It obeys law of conservation of charge. Okay, this is about the Kirchhoff current law. Next will be Kirchhoff voltage law. Kirchhoff voltage law. So this is also known as second law of Kirchhoff. So how can you define this? Same thing, the algebraic sum of voltages or potentials, you can say, voltages in a loop, that is here junction, here loop, is equal to 0. So loop means, let us, here I am considering a loop here. So 1, 2, 3, these are the resistors connected to the voltmeter with a potential, battery plus minus. See, resistors named as R1, R2, R3, these are all connected in the series. Current here is I. So if there are resistors connected in series, means current is same in every resistor. So voltage applied is say V. Now algebraic sum means here across the resistance potential is IR1, IR2, IR3 and this is minus V. So you can write here mathematically. So algebraic sum of voltages across this voltage is IR1 plus IR2 plus IR3. You can put the minus V is equal to 0. This is the formula for this. From this simply you can obtain the relation for the current also. From this I take as the common, we will get current I is equal to V by R1 plus R2 plus R3. This is the formula for the current in the circuit, in the loop. So here it better to write here, it obeys law of conservation of energy. So these are the two laws, Kirchhoff two laws. Now you can, next will be, how can you apply these two laws for obtaining the condition of a wheatstone bridge. Let us see. Here wheatstone bridge, here I am considering 4 resistors having the resistances P, Q, R and S connected as shown in the figure. So the figure will be writing in the simple manner, just like a trapezium, 2 dots, 3, 4 dots is connected with the resistors 1, 2, 3 and then 4. These are the resistors named as P, Q, R, S. Okay. Now we can observe the junctions and all. Here you better to write about the circuit. Here let P, Q, R and S are resistances connected as shown in diagram or figure, whatever it may be. Say these are the points, we can say these are the junctions. This is one loop, so we can apply both the laws here. So for this explanation, the terminals named as, how many junctions are there? Let us say A, B, C, D. Let A, B, C and D are junctions. Now AC is connected to a battery of potential V. Now these two are connected to the battery. Whenever battery is connected to it, automatically the current will flow. So the current will flow like this, I. So next, BD is connected with a galvanometer. Meter have resistance G, let us say. Now these two are connected with a galvanometer G. So what is the purpose of using the galvanometer? It not only show the direction of the current, not only measure the current, but also give the direction of the current also. To obtain the balancing condition, you have to use the galvanometer here. So first of all, here important point here is, this is a junction. Now the current coming from here, positive charge to here, at this point, if it reaches I current, it will be divided into two parts. Let us say in this part I1 current, in this I2 current. Now I1 current going to the point B. Again it will be divided into two ways. One is passing through the Q, that is I1, I2, I3. Now galvanometer current, another is named as IG. Now whenever it reaches the point Q, it will go to this way and reaches the negative. So what about this one? I2 current coming to here point D junction, and then again it will divides into the two parts. Actually the IG's current is coming, so no need to go. It will go in this direction, that is say I1, I2, I3 final and then I4. It will comes to the point C and then come to here. So this is the important point to identify the current directions. Okay now, so once again I would like to repeat this. I current here starting, it reaches the point A, divided into two parts, I1 and I2, and point I1 reaches the B, again divided into two, I3 and IG. It will comes to the C and then come to the negative terminal. So what about from this I2 coming to the D and then IG come to this in this way. So it will both added and becomes I4. It will be going to this direction and will come back to the negative direction. That means here you can apply so many types of loops here. So A, B, C, D are already junctions. Loops means you can use so many loops you can use. A, B, C, D, A, one loop. A, B, D, A, another loop. B, C, D, B, another loop. A, B, C, some V, A. So many loops you can observe here. Among them, for our convenience, you can use some loops to get the condition, balancing condition. First of all, I am using the condition for the first law, current law. Now you can apply any two junctions. No need to use all the junctions. Simply you can use two junctions. Now apply Kirchhoff current law. So we can say at junction, say let us I am considering at a B junction, at a D junction, at a junction B. So what are the incoming currents and what are the outgoing currents? At junction B, incoming currents are I1, outgoing currents are I3 and IG. As we know that from the previous statement, incoming currents can be considered as positive, outgoing is negative. Say at this point, incoming condition is I1. Okay, incoming. Outgoing are minus, that is minus I3 minus IG is equal to 0. So keep in mind. So from this we can write I1 is equal to I3 plus IG for my convenience. Let us say equation 1. Now applying the Kirchhoff current law at junction D. You can write here at junction D. So how many incoming or how many outgoing? Let us say this is incoming current, this is incoming current, this is outgoing current. So you can write here same thing. Incoming is positive, I2 plus IG minus I4 is equal to 0. Or else you can write I2 plus IG is equal to I4. Let it be equation number 2. Now you can apply the Kirchhoff voltage law. So you can write here apply Kirchhoff voltage law. So for this you need the loops. Here for my convenience I am considering the loops A, B, D, A, one loop. From loop A, B, D, A. This is one loop A, B, D, A. Here algebraic potential in a loop is equal to 0. Algebraic potential means you better to use the arrow mark is important here. Look at this one. Here what is the potential across this P resistor? That is I1P. Across this IgG. Across this I2R. Now here starting point going in the positive direction and positive direction. This is in the arrow mark will be in the opposite direction. That we can put minus here. So from this diagram I can write here I1P plus IgG. You can put here opposite direction, that is minus I2R is equal to 0. So for my convenience I1P plus IgG is equal to I2R. Let it be equation number 3. Okay. Next another loop B, C, D, B. So from loop B, C, D, B. This is another loop. From this loop you can use same thing here. Here potential is I3Q. Here in the I4S this is IgG. So if you observe this is coming in this direction, that is positive. Here the arrow mark will be in the opposite direction, so you can use minus. This is also arrow mark opposite, that is minus. So right here I3Q minus I4S minus IgG is equal to 0. For my convenience I3Q is equal to I4S plus IgG. Let it be equation number 4. So among these 4 equations, now to obtain the balancing condition, galvanometer must show the null deflection. So for to balance the bridge, galvanometer shows null deflection. What do you mean with the null deflection? Ig will be 0. Now from equations 1, 2, 3 and 4. So what is equation number 1? This is equation number 1. Equation number 2. Equation number 3. Equation number 4. Now from these equations Ig should be substituted as 0. Ig is equal to 0. That means you will get here I1 is equal to I3. Okay. Next I2 is equal to I4. Keep in mind. Okay, from this above two equations you will get I1P is equal to I2R. This is, see, so to balance the bridge, galvanometer shows null deflection, that is Ig is equal to 0. Now from the equations 1, 2, 3 and 4, I am substituting Ig is equal to 0. That means from this you will get Ig 0 means I1 is equal to I3. This is I2 is equal to I4. This is about the equations here is from 3 equation I1P is equal to I2R. From equation 4 I3Q is equal to I4S. Now dividing the equations 5 and 6. What you will get? I1P by I3Q is equal to I2R by I4S. As we know that I1 is equal to I3, I2 is equal to I4. This cancel. Finally, we will get P by Q is equal to R by S. This is the Wheatstone bridge principle. Balancing condition for the Wheatstone bridge is P by Q is equal to R by S. That's all. Thank you for watching.